Welcome back. In Chapter 1, we learned how machines think. Now, we go one level deeper into the anatomy of an AI system, its vital signs, and the vocabulary you'll need to hold your own in a room full of data scientists. Here's the plan for this chapter, organized around a few key areas of focus. First, we'll dissect the three layers of any AI system: data, model, and infrastructure, and see how APIs and human roles connect around them. Think of it like anatomy class before surgery. You can't audit what you can't locate. Second, we'll master the metrics: accuracy, precision, recall, F1, confusion matrices, and AUC-ROC. These sound intimidating, but I promise, with a couple of real life stories like a spam filter and a cancer screening test, they'll feel like common sense by the end. Third, we'll decode the language of AI: weights, parameters, tokens, embeddings, RAG, fine tuning. The terms that fly around in technical meetings, explained in plain words you can actually use. And finally, we'll connect it all back to your job, understanding how design choices made by engineers quietly create constraints and risks that you, the auditor, will inherit. By the end of this chapter, you'll walk into an AI audit meeting and actually enjoy the conversation. Stay with me. And if you're finding this series useful, a quick subscribe helps more learners find it too. Let's dive in. Let's start with a simple mental map that will serve you for your entire AI audit career. Every AI system, no matter how fancy, has three layers: data, model, and infrastructure. Miss any one of them in your audit scope, and you've left a door unlocked. Think of it like a restaurant. The data layer is your ingredients, where they're sourced, how fresh they are, how they're stored. The model layer is the chef and the recipe, the actual intelligence turning ingredients into dishes. And the infrastructure layer is the kitchen itself, the stoves, the plumbing, the delivery vans. Now here's a question for you. If customers are falling sick, which layer do you inspect? Exactly, you can't know in advance. You have to be able to examine all three. The data layer covers collection pipelines, storage, quality checks, and access controls. Most AI failures I've seen in practice were born here, long before any model existed. The model layer covers algorithm choice, training, versioning, and validation, the brain of the operation. And the infrastructure layer covers the servers, cloud platforms, APIs, and deployment pipelines that keep it all running. Here's why this matters practically. When something goes wrong, teams love pointing at other layers. The data team blames the model team blames infrastructure. Your audit scope needs to cover the handoffs between layers because that's where accountability quietly evaporates. Keep this three-layer map in your head. Every lesson in this chapter plugs into it. Here's something that surprises many new AI auditors. The model itself is often the smallest part of the system. What surrounds it, the plumbing, is where risks multiply. Let's talk about APIs and integration points. An API is simply a doorway through which software talks to other software. When your banking app checks whether a transaction is fraudulent, it isn't running the fraud model on your phone. It sends a request through an API to a model hosted somewhere else and gets a score back in milliseconds. Simple enough. But now imagine that fraud score feeding into 5 downstream systems: the payment gateway, the customer alert service, the case management tool, the reporting dashboard. That's a dependency chain, and every link is a place where things can silently break. Let me share a real pattern I've seen. A company updated its model to output risk scores from 0 to 1 instead of 0 to 100. Technically a small change, but a downstream system still expected the old scale. So a score of 0.9, which meant high risk, was read as nearly zero risk. Fraudulent transactions sailed through for weeks. No alarm went off because every individual system was working exactly as built. So what do you ask as an auditor? Who consumes this model's output? Is there a documented inventory of integrations? What happens downstream if the model changes, goes down, or starts returning garbage? Is there a contract, a version specification between systems? Remember this phrase: the model may be smart, but the plumbing is dumb. And dumb plumbing with smart water flowing through it is where audit findings live. We've covered the technical layers. Now let's talk about the layer that actually decides whether AI succeeds or fails: the humans. Every AI system lives inside a human ecosystem, and if you audit the technology but ignore the people, you've done half an audit. Picture three groups standing around any AI system. First, the builders: data scientists, ML engineers, data engineers. They collect data, design models, and tune performance. Their incentive is usually accuracy and delivery speed. Second, the operators: the ML ops teams, IT operations, and model risk folks who keep the system running, monitor its health, and handle incidents. And third, the users: the loan officers, doctors, HR recruiters, or customer service agents who act on what the AI says, and the customers on the receiving end of those decisions. Now, here's the question I always ask in fieldwork: when these groups disagree, who wins? I once interviewed loan officers at a lender using an AI credit model. Several admitted they'd stopped questioning the model's rejections, even when their experience screamed otherwise, because overriding it required a three-level approval. The builders had created a good model. The process had created blind obedience. No technical test would ever have caught that. There's also a fourth, quieter group: the accountable executives. Someone must own the risk. Often, everyone assumes someone else does. So in your audits, map the humans just like you map the data flows. Who builds, who runs, who uses, who overrides, and who answers when it fails. If any of those boxes is empty, you've already found your first observation. All right, time for the metrics that appear in almost every AI audit, and trust me, in your AI exam too: accuracy, precision, recall, and F1. Sounds dry? Let me tell you a story about email and it'll all click. Imagine you build a spam filter. Accuracy asks a simple question: out of all emails, what fraction did you classify correctly? Sounds sufficient, right? But here's the trap. If only 2% of emails are spam, a lazy filter that marks everything as not spam scores 98% accuracy while catching zero spam. Impressive number, useless system. This is why auditors should never accept accuracy alone, especially with imbalanced data like fraud, disease, or defaults. So we need sharper questions. Precision asks, of everything you flagged as spam, how much was actually spam? Low precision means genuine emails, maybe your client's contract, land in the junk folder. Recall asks the opposite. Of all the real spam out there, how much did you actually catch? Low recall means phishing emails reach your inbox. Notice the tension? Tighten the filter and precision rises, but recall falls. Loosen it and the reverse happens. It's like a security guard at a mall. Stop every visitor and you'll catch every thief, but harass hundreds of innocent shoppers. Stop nobody and everyone's happy until the theft report arrives. The F1 score simply balances precision and recall into one number, useful when both kinds of mistakes matter. Your audit question is never which metric is highest. It's, did the business choose the right metric for the harm that matters most? That choice is a governance decision wearing a mathematical costume. Now that you understand precision and recall, let me show you where those numbers actually come from. The confusion matrix. Despite the name, it's the least confusing tool in AI, and once you can read one, you can interrogate any classification model on Earth. Picture a simple 2x2 grid for a medical screening AI. Down one side, what the model predicted: disease or no disease. Across the top, the truth. That gives 4 boxes. True positives: sick patients correctly flagged. True negatives: healthy patients correctly cleared. False positives: healthy people wrongly flagged, who now face anxiety and unnecessary tests. And false negatives: sick patients the model missed, who walk home reassured while the illness progresses. Here's the auditor's insight. Those 4 boxes are not equally costly. In cancer screening, a false negative can be fatal, while a false positive is stressful but survivable. In fraud detection, a false positive might freeze an innocent customer's salary account on rent day. So when a client shows you a single glossy accuracy figure, ask to see the full matrix. The harm hides in the boxes they didn't mention. Now, AUC-ROC. Fancy name, simple idea. Remember thresholds from chapter 1? A model gives probabilities and someone picks a cutoff. The ROC curve shows how the trade-off between catching true cases and raising false alarms shifts across every possible threshold. The area under that curve, AUC, summarizes it. 1.0 is a perfect model, 0.5 is a coin toss. Your takeaway? A strong AUC means the model can discriminate well, but the chosen threshold decides who actually gets hurt. Audit both. Let me introduce you to the two classic ways a model fails at learning: overfitting and underfitting. And the best way to understand them is to think about two students preparing for the AAIA exam. The first student memorizes every practice question word for word. Ask him those exact questions and he scores a perfect 100. But change the wording slightly, present a new scenario, and he collapses. He didn't learn concepts, he memorized answers. That's overfitting. The model has learned the training data so intimately, including its noise and quirks, that it can't generalize to anything new. It looks brilliant in testing and fails in the real world. The second student barely studies at all. She skims one summary sheet and walks in with only the vaguest grasp. She fails the practice tests and the real exam alike. That's underfitting. The model is too simple to capture the real patterns in the data. It's consistently mediocre everywhere. Now, why do both fail audits? Because both produce a dangerous gap between reported performance and real performance. I've seen a vendor demo where a model scored 99% in the lab. When we asked how it performed on data it had never seen, the room went quiet. That gap between training performance and unseen data performance is your single best clue. So here's your audit question, beautifully simple. Show me the model's performance on training data and on truly held out data side by side. A large gap screams overfitting. Uniformly poor numbers suggest underfitting. And a refusal to show both? Well, that's a finding in itself. Let's build your AI vocabulary today. Because in technical meetings, these 5 words fly around constantly. Weights, parameters, hyperparameters, tokens, and embeddings. Miss them and you're a tourist. Know them and you're a participant. Start with weights and parameters, which people use almost interchangeably. Think of a massive sound mixing board in a music studio with millions of tiny sliders. Each slider slightly changes the final sound. Training a model is the process of nudging all those sliders until the output sounds right. Those sliders are the parameters and their positions are the weights. When you hear that a language model has 70 billion parameters, it means 70 billion sliders were tuned during training. Hyperparameters are different, and here's the distinction that matters. Parameters are learnt by the machine. Hyperparameters are chosen by humans before training begins. Things like how fast the model learns or how complex it's allowed to be. Human choices, human accountability, and yes, human audit trail. Ask who set them and how. Now tokens. Language models don't read words the way we do. They chop text into small chunks called tokens, roughly 3/4 of a word each. Why care? Because usage, cost, and even context limits are measured in tokens. When a vendor bills per token, that invoice is an audit artifact. Finally, embeddings, my favorite. An embedding converts words or documents into lists of numbers so that similar meanings sit close together, like arranging books in a library by theme rather than alphabet. That's how AI knows doctor and physician are neighbors. 5 terms, 1 vocabulary lesson, and you're ready for the next meeting. Here's a practical question organizations face every day. We want AI that knows our business, our policies, our products. Do we build a model from scratch? Almost never. That costs millions. Instead, they adapt existing models. And today, we'll cover the three main ways they do it. This comes up constantly in audits now. First, transfer learning, the umbrella concept. Take a model trained on a massive general data set and adapt it to your specific task. Think of hiring an experienced chartered accountant and teaching them your company's specific processes rather than training a fresh graduate from zero. The general expertise transfers, only the specifics need work. Second, fine-tuning, which is transfer learning in action for language models. You take a pre-trained model and continue training it on your own data, your support tickets, your contracts, your tone of voice. The catch? Your data is now baked into the model's weights. If personal or confidential data went in, extracting it later is nearly impossible. Remember that when we reach privacy chapters. Third, and this one is everywhere now, RAG, Retrieval Augmented Generation. Instead of retraining anything, you give the model a live library. When a user asks a question, the system first retrieves relevant documents from your knowledge base, then the model answers using them. Like an open book exam instead of memorization. It's cheaper, more current, and easier to govern. But now, your audit must cover the library too. Wrong documents in, confident wrong answers out. So when a client says, we customized an AI, your first question is simple. Fine-tuned or RAG? The risk profile and your audit plan differ completely. Let's talk about a skill that sounds like jargon, but is really just clear communication. Prompt engineering. A prompt is simply the instruction you give a generative AI. And it turns out, how you ask changes what you get, sometimes dramatically. For auditors, this matters in two ways. You'll audit systems built on prompts, and you'll use prompts in your own work. Think of it like briefing a very capable but very literal junior colleague. Say, summarize this report, and you'll get something generic. Say, summarize this report in 5 bullet points for a board audience, highlighting financial risks and using no technical jargon, and you'll get something useful. Same colleague, better briefing. The model didn't get smarter, your instruction got clearer. Now, here's where the audit angle comes in. Many enterprise AI applications are essentially a commercial model wrapped in a carefully crafted system prompt, a hidden instruction that tells the model who to be. You are a polite banking assistant, never discuss competitor products, never give investment advice. That hidden prompt is a control. So ask the questions you'd ask of any control. Who wrote it? Who approved it? Where is it version controlled? How is it tested? Can employees quietly change it without review? I've seen organizations where the system prompt, effectively the policy engine of the chatbot, lived in one developer's laptop. Imagine your loan policy existing only in one officer's memory. And one caution for your own practice. Never paste confidential audit evidence into public AI tools. Your prompt may become someone else's training data. Clear asking, careful sharing. That's prompt discipline for auditors. Let's close this chapter with an idea that ties everything together. The design choices engineers make early in an AI project quietly decide what you, the auditor, will and won't be able to verify later. In other words, auditability isn't something you bring to the engagement. It's something the system either has or lacks. Let me make that concrete. Suppose a team chooses a deep neural network over a simpler scorecard. That's a design choice, and it means individual decisions may never be fully explainable. Suppose they don't log model inputs and outputs to save storage costs. Another design choice, and now you cannot reconstruct what the model decided last quarter. Suppose they use a third-party model through an API. Now the training data, the weights, the very brain of the system sits behind another company's walls, forever outside your direct evidence. See the pattern? Each choice was reasonable from an engineering or cost perspective. But stack them up, and you get a system where the honest audit answer to what happened and why is, we cannot know. I once had to write exactly that sentence in a report, and believe me, Boards do not enjoy reading it. So here's the mature auditor's move. Don't just audit AI after it's built. Push for audit requirements at design time. Logging standards, explainability expectations, documentation gates, contractual audit rights with vendors. It's the difference between designing a building with fire exits and trying to add them after the concrete sets. That completes our anatomy lesson. Next chapter, we follow the AI lifecycle from raw data all the way to retirement. See you there.